Good afternoon, everybody. This live stream today is focused on the Lake Effect Snow Machine. Very active Lake Effect Snow Machine right now off of Lake Ontario. You can see the core of this band hammering areas like Pulaski up towards Sandy Creek. That's I-81. So if you're heading northbound out of I-81 out of Syracuse and you encounter this band, visibility is going to drop to near zero. You've got snowfall rates in excess of 3 inches per hour, even the possibility of thunder and lightning within this band. And you can see little gravity waves as well as this convection is powered up by the very warm lake temperatures. They are relatively warm this time of year because we haven't had very much in the way of Arctic blasts so far in the eastern U.S., so it retains those lakes as relatively warm. Lake Ontario is a pretty deep lake, at least compared to Lake Erie, so it doesn't really freeze over. Even if you did get a lot of those Arctic blasts deep into the winter season, you just don't get as much of a freeze over on Lake Ontario as you do on Lake Erie. But so far, it's been a very warm winter here across the central and eastern U.S., and that also keeps the lake temperatures very warm and ice-free, and that helps to increase the temperature difference between that lake temperature and the air just above the surface. And usually you want at least a 10-degree Celsius temperature difference between that lake surface, which is certainly above freezing. We'll take a look at the lake temperatures. We'll take a look at those 850 temperatures. Also, another factor that's very important for lake effect snow is the inversion height. And basically that's the inversion is when you have a little warm slot of air just above the ground. That can act as a lid on the atmosphere and can prevent this convection from growing up tall into the troposphere. When you have more shallow convection, then you'll have less in the way of those prolific snowfall rates. And you can see these individual convective bubbles that form over the lake. Just little towers, convective towers. Sometimes you can even have water spouts. I saw a water spout on Westville, New York during a lake effect snow warning. That was on Lake Erie. Made landfall too. That thing came ashore, coming ashore off Lake Erie, basically became a tornado there during lake effect. So you can generate very strong instability over the relatively warm Great Lakes, especially when you get those cold temperatures just above the ground, minus 10 degrees Celsius or so, negative teens at about 850 up to 700. More than sufficient to generate this plume. And look at how it's more convective, individual convective elements, and then becomes more laminar downstream as this thing is just pounding Sandy Creek and the Richland area. Lake effect snow warnings are in effect for this monster plume here. It's also hammering the Tug Hill Plateau, which is an area of elevated terrain just to the east of Lake Ontario. It's called the Tug Hill Plateau. It's one of the snowiest locations anywhere in the world. And you can also get some help with these lake effect events by orographic lift. So this moisture plume coming off the end of Lake Ontario like a fire hose is forced upward on the western slope of that Tug Hill Plateau, squeezes out even more precipitation. You have a little bit of a boundary here as well that's starting to sag south. So usually these bands will shift a little bit north ahead of a little vort and then come back south again on the backside of that vortex as those winds will shift to a more west-south, west-northwesterly direction. Another factor that's important to maintain a band like this is reduced wind shear. So you want unidirectional flow with height, and it needs to be parallel at all levels in the lower atmosphere up to about 3 kilometers. And you start to introduce wind shear, and then this band will break up into little supercell structures, and you get more of a convective evolution of the band. You'll get those snow squalls that come in waves, little popcorn variety storms with whiteout and grapple, lightning strikes happening. But if that wind shear is reduced and you have unidirectional flow in the low levels of the atmosphere, then you get the organization of this single dominant band down the length of the lake. But it also matters that on the shape of the lake. So you need the flow to be parallel to the main axis of the lake. On Lake Ontario, the main axis is oriented west to east. And so if you had northerly flow that was down the minor axis of the lake, then you'd get the organization of multiple small bands down the south end of the lake, each one of those not packing as much of a punch. But when you get the flow that's oriented parallel down the length, the main axis of the lake, then the relatively warm waters of the lake create what's called a thermal low. So you get the formation of a subtle low pressure right at the surface, and that causes these westerly winds to converge from the land toward the center of the lake. And that helps to create convergence down the center of the lake as well. As these winds converge, they will form a single dominant band down the length of the lake of Lake Ontario. And this is definitely a textbook lake effect event. One of the more textbook lake effect events that we have seen in a couple of years. It seems like this pattern over the last couple of years has not been incredibly favorable for that lake effect snow. And I have this video here that I've been playing you. This is from the Buffalo Lake Effect Snow Emergency in 2014. One of the most intense snowstorms, winter storms I've ever covered. Absolutely crippling snowfall rates, 5 to 6 inches per hour. You can see snow plows there getting stuck in the core of that band. We had a hotel there at the Best Western down at Lackawanna on the south towns of Buffalo. Ended up getting bed bugs inside of that hotel, but left the hotel, left our supplies in the Best Western. This is before we realized that our room was completely infested by bed bugs, and then drove out so Maria could do a live shot for Fox out there inside of the core of this band. And we were never able to get back to the hotel. The band was so intense. It's like a tornado damage path that you just can't penetrate. The snowfall is so incredibly prolific. And there was actually loss of life from this snowstorm. So people that would leave their homes wearing shorts and a t-shirt before the Arctic blast arrived, and then the Arctic blast came and that snow band arrived, whiteout conditions, they got trapped in their car, temperatures plummeted so low that it became a survival situation in those vehicles, and the snow was so heavy that rescue workers were not able to reach those people. And very sadly, those people froze to death in their cars. And it shows you how impactful these lake effect snow bands can be as well. Just outside of the band, sunny skies, crisp bluebird skies as well. But then you go inside of the band and the heaviest snowfall rates that you've ever witnessed, 5 or 6 inches per hour, thunder, snow, thunder and lightning, frequent thunder and lightning. And this thing lasted for about 4 days. So this was all centered around that November 17 period for 4 days. 8 to 9 feet of snow fell from this individual event. And eventually I had to go to Walmart, get a one-piece snowsuit, and then I went on foot and started walking through that feet of snow. There were these packed down trails through the snow, little tunnels, and I was able to get back to the Best Western. And I had walked so many miles, was covered in sweat. I fell down on the bed, took off the one-piece snowmobile suit that I just purchased at Walmart, and the bed bugs must have smelled it because they came out of the crevasses on the sheet that was around the edge of the bed and just started lighting me up in my sleep. I woke up, streaks of blood all over the sheets. I saw every single life cycle of those bed bugs. I saw nymph, I saw adult. They were just all crawling around. After they had just lit me up, I had bites all over my arms and everything. That was the Best Western there in Lackawanna, New York. And they eventually ended up giving me my room for free if I didn't tell anybody about the bed bug infestation. But there were millions of them caked in every little crevasse along that skirt at the base of the bed inside of that hotel room. But everybody coming together, snowmobiles out there, people bringing their bobcats to help to try to clear the snow. But definitely the most crippling snow event that I've ever chased. This one here is certainly not going to be persistent like that. If this lasted 4 days, and you'd be talking about 8 or 9 feet of snow crippling out here off Lake Ontario. It is a lot more populated downwind of Lake Erie, however, but the main axis of the lake is oriented more southwest and northeast, so this westerly flow just not quite down the main axis of the lake, but still getting some significant snowfall there off that Chautauqua Ridge. There is an area of slightly elevated terrain here, far western New York, called the Chautauqua Ridge, that can also help to squeeze out some of that moisture. So let's look at some of the basics here of lake effect. And I first want to show you this hodograph. Hodographs could also be used for lake effect forecasting as well. And here is the hodograph that is out of the radar site just downwind of Lake Ontario. And you can see this unidirectional flow, your 1 kilometer wind out of the due west at about 25 knots, your 2 kilometer wind basically out of the due west, slightly out of the north at about 30 knots. Basically unidirectional shear, limited wind shear, directional shear from the surface all the way aloft. And also we do have these watches and the warnings, lake effect snow warnings downwind of Lake Ontario with that west-northwesterly flow down the main axis of the lake. 2 to 3 feet of snow expected along that path. And so basically the temperature difference between the surface and 850 millibars is a good metric to use here over the Great Lakes. There you can see that those low-level lapse rates, the importance of those low-level lapse rates, and how steeply the temperature decreases with height from the surface of the lake temperature up to about 1 kilometer. Of course, you can get lake effect downwind of the Great Lakes. You can get it downwind of the Great Salt Lake. You can also get ocean effect. Some of the most prolific lake effect snow anywhere in the world happens off the Sea of Japan in northern Japan. Big mountains as well up there. Just prolific multiple band ocean effect with extreme instability off that lake. And the temperature difference between those temperatures about 1 kilometer above the ground or at 850 millibars, where they are in the negative teens today, and the temperature of the lake, which is above freezing, in this case, plus 3 degrees C. So the difference between the lake surface temperature and the temperatures just above the ground, those are your lapse rate statistics for lake effect. And in general, you really want that double-digit temperature difference between the lake temperature difference, between the lake temperature. So we can look at Lake Ontario current temperatures right now and see exactly what those temperatures are. We've got current temperatures here, Great Lakes. Lake effect snow machine. I used to chase this lake effect snow machine all the time back in the day, especially when I was living in New York City out there. It was a pretty easy drive out to these Great Lakes to intercept these nasty bands. You'll intercept them. Suddenly you get those whiteout conditions. And so really quickly, I want to break down the inversion height here as well. But first we're looking at those Great Lakes current temperatures. Got it. Right here, Great Lakes portal, nice. Wow, Lake Ontario, very warm. So the temperature right now in Lake Ontario is about 45 degrees. So that is very warm. And then you look above at 850 millibars. You have that unidirectional flow. You do have that perfect pattern for the lake effect with the East Coast trough. Let's look at the inversion height. Ooh, there it is. Temperature at 850. My God. It's minus 15 to minus 20 right now. And there you can see the temperature at 850 millibars. This is what is fueling this lake effect event. The purple there, minus 20 degrees C at 850. So you're talking about a 44 degree sea surface temperature there. So Great Lake over Lake Ontario. So that is way more than a double-digit temperature difference between the lake surface and aloft. Your inversion height, there you can see your inversion height, about 2 kilometers. So this is your inversion height. Notice how in the sounding, and let me slide this over to the right. This is how you can assess the inversion height of the profile. See how your lapse rates are very steep all the way up, and then boom, suddenly the temperature increases. So that's your inversion height. And generally, if it's higher than 1 to 2 kilometers, you're going to be in business for your lake effect snow. Look at this unidirectional profile as well that's being indicated by those models. You superimpose, though, about a 44 degree surface temperature over that, and you are talking about 20 degrees, a 20 degree temperature difference between the surface and 850 millibars, and you modify that surface temperature out to that lake temperature. That's what gives you that low-level CAPE, an abundance of low-level CAPE. You've already got 221 surface-based CAPE here just by this profile with a slight modification of that lake surface temperature, but even just warming up into the 20s there, you're already talking about 220 Cape. That's with your inversion height up just below 3 kilometers. And that is this morning. So you forecast out with time through this evening. And you can also still see what your inversion height's going to be. See how it changes over time. And look at that, your inversion height. You have a little bit of a subtle inversion that develops at about 2 kilometers. But then above that, you kind of get an erosion of that inversion aloft. So basically, you retain those low-level lapse rates all the way through the event. Looks like we start to get a little bit of directional shear, though, through this evening. So this evening, you may see that band start to break up a little bit. But in general, some pretty unidirectional flow there over the lake. And that's certainly helping to contribute to that big-time lake effect snow that's going to be happening. And we are definitely transitioning into a pattern that is cold in the eastern U.S., and we get a ridge that forms in the western U.S. as well. That's associated with what's called a positive PNA. So here you can see your global pattern. There's North America, and we're getting this transition to a ridge trough pattern from west to east across North America with a ridge in the western U.S., a trough in the eastern U.S. And if we start to get a ridge that forms up near Greenland, that's a blocking pattern that will help maintain this trough in the eastern U.S. It'll also help an upper level system or a coastal storm to move up the east coast, and you help to get more of that buckled upper level pattern. You can also see this jet stream with an Arctic connection coming up from near the North Pole up north of the Arctic Circle. That's your Arctic air mass injection with this eastern U.S. trough. And this is a positive PNA, it's called here, the Pacific North Atlantic Oscillation. When you get a ridge that forms in the Pacific Northwest like this, with a trough in the eastern U.S., this is a prime pattern to get lake effect downstream of the Great Lakes because of those relatively cold temperatures just above the surface. And there are your cold 850 winds that are moving over those relatively warm Great Lakes waters. The water temperatures are actually the warmest over Lake Ontario as well. Lake Erie starting to cool off a little bit faster. Lake Superior is also a prolific lake effect generator of those lake effect snows. And looking at the long range, there has been some discussion of a potential southern U.S. snowstorm toward this weekend. And I haven't touched it yet still because it is just a little bit further out. But we do have the overall pattern in place for a coastal storm with this eastern U.S. trough, a positive PNA building in as well across the Pacific Northwest with that ridging, persistent ridging. And you also get these Alberta clippers that are coming on the east side of that ridge, individual troughs, little troughs that will amplify as they move into that large-scale eastern U.S. trough. And look at this blocking starting to form downstream over Greenland by next weekend. That is that negative NAO, North Atlantic Oscillation, basically acting as a dam for the jet stream over the Atlantic that encourages this buckling of the jet. So you do have the general eastern U.S. trough. You do have these injections, these Alberta clippers that are riding that ridge on the east side of the ridge. And those are candidates to become coastal storms with proper phasing. And then that coastal storm will ride that temperature gradient on the western side of the Gulf Stream all the way up. But a lot has to happen. You need it to be perfectly timed with this blocking downstream. You need to have these troughs that are riding down these Alberta clippers. This one looks like a candidate to potentially bring some winter weather to the southeastern U.S. and even the Carolinas. So look at that on Saturday, moving through the Carolinas and that southeastern U.S. up into the southern Appalachians there as well. That could be an issue. That southeastern U.S. coastal storm there rips up the east coast. And you do have that blocking upstream across Greenland. Tries to get that vertically stacked system over the northeast U.S. But that looks like a candidate to be a coastal storm right there. But you can see how complex this system is. You've got this closed upper low that's anchored over the Canadian Maritimes. You have a continuous injection of these Alberta clippers riding that ridge from northwest to southeast. This looks like a very favorable pattern for continued lake effect snows downwind of Lakes Erie and Ontario. It's also a good candidate for southern U.S. snowfall, east coast snowfall, northeast as well. but the exact tracks of those individual storms, we're still going to have to wait. And I'm not the best at forecasting East Coast snowstorms. There are people that absolutely dominate at forecasting these, even down to on the subseasonal and seasonal timescales as well. But you can kind of see the tendency for the formation of these coastal lows given this pattern. Dominating anticyclone there off of Greenland as well. But I am a lot better at the smaller scale meteorology, mesoscale meteorology like lake effect, storm chasing, launching rockets into tornadoes. I'm just not as good at the synoptic scale, but I still try to forecast. My PhD dissertation was on seasonal climate variability and deriving Pacific Ocean sea surface temperature patterns and determining the climate teleconnections downstream across North America. We're just so blessed to have the largest body of water that is the Pacific Ocean conveniently located upstream of North America. So we can use it as a predictive mechanism on the seasonal, even all the way up to the decadal timescales. We have that La Nina that is dominating the Pacific right now and that cold PDO. And that's why we do expect this spring to be relatively active across the Mid-South. We did have a couple of bird fart tornadoes yesterday near McKenzie, Alabama, back to the west, about 10 miles to the north of Evergreen. Probably should have gone out there to chase that event anyway, to provide that ground truth. I did see there were a couple storm chasers that were out there across the Mid-South, but it still didn't go as big. And I think that those bird fart tornadoes only happened because of the development of that kicker storm. So you had that elevated supercell that developed right behind that lead supercell that helped to enhance that low-level jet just ahead of it, helped to enhance the low-level shear in the ambient environment that bean-shaped supercell was embedded within, and certainly did help to tip the low-level wind shear just on the side that was supportive of a brief tornado threat, relatively brief and weak tornadoes. But look at this. Lake effect snow plume. Looks like it's moving up a little bit, but you can see the hint of a boundary, a bit of a wind shift that is moving in here. I do expect these winds to shift to a little bit more northwesterly as we go through the evening, and that should bring this band a little bit closer to Oswego. A meteorology school is located there, SUNY Oswego. A lot of lake effect enthusiasts there as well, probably driving to the north to get a look at this band. Usually the heaviest snowfall rates are a little bit inland from the lake and right along the immediate shoreline. Those relatively warm Lake Ontario temperatures can even mix over that snowfall to a little bit of rain, especially in the early season. However, during the heart of winter now, where you have these temperatures that are into the negative teens just above the ground and equally as cold at the surface, you're not going to get that along the immediate shoreline, but you are going to get slightly reduced snowfall totals as well. Temperatures right now in the teens on the backside of the system, and you can even see how the winds like to converge toward that thermal low near the center of the lake. You can see on the south side of the lake a little bit more of a southerly component, north side of the lake more northerly winds as well, all flowing toward that diabatic heating max that is Lake Ontario, and possibly could get up to 3 feet of snow on the western slopes of the Tug Hill Plateau, southwestern slopes, just east of the Pulaski area to the east of I-81. But I-81 is absolutely getting hammered right now. Visibility is dropping to 0 downwind of Lake Ontario. So pretty interesting lake effect snow regime that is happening right now. Inversion heights at about 2 to 2,500 feet above the ground. That's why you're getting convection that is going all the way up to about 3,000 feet. We can look at the echotops of these individual storms, and you can see a couple little blues out there. So you're probably talking definitely echotops slightly below 10,000 feet, and looking at the inversion height, these echotops are probably closer to about 3,000 feet. But it does look like that inversion does lift as we go through the evening, so it's possible that we could even get some thunder, definitely some more intense snow bands that are moving in, more convective snows as well. Here is that special weather statement. The lake effect snow band is intensifying while slowly edging northward. So it's probably going to edge a little bit north through the day, and then as you go through evening, it should come back down as those near surface winds start to shift and develop more of a northerly component. So just a beautiful lake effect snow event well underway here. There it is in all its glory. Looks like a wind shift trying to settle down here as well. You can look upstream and see what these echoes are doing upstream. It does look like not much of a wind shift over central Ontario. Looking upstream, those echoes are all basically west to east, maybe a slight northerly component, right down the main axis of the lake. We call this fetch. When you have a longer fetch, that means that the winds are going over the main axis of the lake. They're traveling over those warm lake waters a lot more long of a time period. And boy, look at that thing snaking in there. You can even start to see little tornado-like vortices, little water spouts that could develop in there. Look at these little couplets that are upstream. And the Doppler on wheels has even been deployed out here for a research mission to try to measure these little water spouts and couplets that can happen. Usually when you get a little bit more wind shear, and especially some directional shear between the surface and about 2 and 3 kilometers up, that's when you'll get a more cellular nature to the lake effect snow band, and you can even get little mesocyclones embedded within that snow band moving west to east off the end of Lake Ontario. There you can see that convergent band. Winds to the south of the band, a little bit more west, southwesterly. Winds north of the band, more of a west, northwesterly component. Definitely a textbook convergent band there off the end of Lake Ontario. So there it is, 2 to 3 feet of snow expected. And I am going to keep an eye out for that coastal storm in the southeastern U.S. And if it does materialize there in the upstate Carolinas, I'll be heading back that direction. And I'm going to be heading back that direction anyway to reunite with Gizmo as well. So I am excited about that. But there is that snow band dominating. Thank you, everybody, for joining this morning weather briefing. A little bit of a shift of gears toward a lake effect snow insanity. LES is the abbreviation for lake effect snow. And we do have an absolutely monster plume heading off Lake Ontario, pounding those areas like Pulaski. I've stayed a lot in that Super 8 in Pulaski there on I-81. It's a cozy little place, and it looks like the band is heading a little further north. Now the core of it is over Sandy Creek with those 3-inch and greater per hour snowfall rates hammering Sandy Creek a little bit east of there out towards Smartville, especially the radar site, which is up on that Tug Hill Plateau, really getting hammered out there, probably even pushing 4-inch per hour in the core of that band on the western slopes of the Tug Hill Plateau, squeezing out that snow even more. So thank you, everybody, for tuning in to this weather report. I'm going to monitor the forecast models very closely, and I will do another weather briefing on the potential for a coastal storm, another coastal storm with that favorable pattern. Positive P&A, Alberta Clippers coming down the east side of that ridge, eastern U.S. trough, a blocking high that develops near Greenland. All of that could come together to increase the likelihood of an east coast storm, but it still is a little bit too early to break down the exact track or just how far south into South Carolina that snow event will happen. So thank you, everybody, for tuning into this weather report. Never stop chasing.